Exponential decay. Let's take a look at that. So what's happening now is we're losing stuff. We're not gaining. So this is the same formula. You have your amount. You have your initial amount. You have your decay rate. This is the elapsed time. How much time goes by for us looking at this? But this is the specific decay rate time for the function. Each element, if it's a radioactive element, has a different decay rate. That's why some of them are really, really dangerous for you and others aren't. If the decay rate is really high, it gives off a lot of energy. That's dangerous. If the decay rate's really slow, it doesn't give up much energy. We can use it. Carbon dating, you've heard of that in the news. That's where we look for radioactive carbon in living things. We know how quickly it decays. That's how we can tell how old something is. When we take a bone out of the ground and we carbon date it, we find out how much radioactive carbon there is in it, which doesn't hurt us, and we can tell how long it's been around in the ground. So that's just a little bit of an idea. So half-life is the time it takes for a quantity to decrease to half its amount. What would doubling time mean? Doubling time would be the time it takes for an item to double its size in time. So then there's all sorts of things like quadrupling time or fifth timing, but that doesn't make sense. But you would say that it has a half-life of 1/5. Okay. Let's look at an example. Oh, look, my carbon example that we were talking about. Living organisms contain two types of carbon. You have carbon-12 and you have carbon-14 in your bodies. You really do. And that carbon is in your bones, and it's in all sorts of things. So when an organism dies, the amount of carbon-14 doesn't go up anymore because you're dead. You're not eating anything. You're not doing anything. You're dead. But the carbon-14 decreases exponentially with a half-life. So once you're dead, we can measure how much carbon-14 you have in you, and depending where it is, we can tell how long you've been dead. So this half-life is about 5,730 years. So it takes 5,730 years for half of the carbon-14 in your body to be gone. One can measure the amount of carbon-14 left in an organism to estimate how long ago it died. The decay process is modeled using this function, where P represents the percent of carbon-14 remaining, and little t represents the time in years. So we're going to find a pine fossil, and it was found in western United States, and it shows that it has an age of about 6,000 years using carbon dating. What percentage of carbon-14 is left in that pine needle? Well, we're going to go to the formula. And it says that this thing was about 6,000 years old. Well, that means that that's the elapsed time. So that's going to go in for little t. This is the time for the function. We don't get to play with that. That's carbon-14. That has a half-life of 5,730 years. We can't play with that one. This is the half-life. This means that half amount is remaining every 5,730 years. And this is our starting percent. You start with 100% of something, right? That's what percent means. So that's our starting amount, 100%. Now notice, it hasn't been a full 6,000 years, has it? So I'm not putting, no, sorry, let me go back. 6,000 years is longer than 5,730, isn't it? It's longer than that, which means we would expect that it's gone through one complete half-life and a little bit. So we're expecting there to be less than 50% remaining. Does that make sense? Every 5,730 years, it halves. So with this, if we thought that it was only 5,730 years old, we'd expect 50% remaining. If we thought that it was two of these, if we thought that it was 11,460 years old, we'd expect there to be a quarter remaining, half of a half. If we thought that it was 5730 times 3. If we thought that it was 17,190 years old, well, that's 3 half-life periods, isn't it? So we would expect the first half-life to take us from 100 to 50, our second half-life to take us from 50 to 25, and our third half-life to take us to 12.5% remaining. Do you see how that's working now? Okay, so we're going to have 100, 1/2, 6,000 divided by 5,730. So that is a little bit more than 1 complete half-life. So I'm expecting a percentage a little bit less than 50%. 6,000 divided by 5,730 equals, I got to do something with that. I think I'll put it into my memory if I remember. I'm not so good with that. So I'm going to take it and write it down. And I'm going to take all the numbers that I can. I'm going to take 1/2, which is 0.5, to the exponent. I'm going to write in all those numbers I had. If you have a more complicated calculator, you might be able to do it easier. But I get an answer for this of being 0.48 blah, 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 times 100. And I'm getting 48% approximately. 48.3% approximately, which is what I thought that we'd come up with given how much time had passed and what the half-life was. I'll pause the video here and I'll be right back.